Yeah, thank you, Jimmy. Yeah, so hi everyone, my name is Huy. I'm from the University of Adelaide, and today I'll be presenting my work in CVPR 25. It's called Interactive Medical Image Analysis with Concept-based Similarity Reasoning. Yeah, so we know that applying AI in medical imaging usually face hesitation from radiologists. This hesitation mainly comes from the fact that AI model is a black box, which they cannot interpret its prediction process. And the second factor is that it is when the model gives prediction, the radiologist cannot provide feedbacks or interact with the model. This is very different from radiologist consultation session, where radiologists can discuss or consult with another on a case for the final diagnosis decision. Hence, in this work, we propose a framework that is both interpretable and interactive to address those two concerns, with the goal to improve trust in adoption of AI in medical imaging. And it's called Concept Similarity Reasoning Model, and it can interactively focus on clinical relevant area as instructed by radiologists. So given a test right here, the CSR will compare the node here with the node from the past case to yield a similarity score of 0.8. It also will compare with other interpretable concepts like fracture or pleural effusion, but it is not shown here for brevity. So we can see that those two nodules has the similarity score of 0.8, and there are no fracture or pleural effusion because their score is really low of 0.1 for fracture and 0.01 for pleural effusion. And this score will be aggregated with the weight of the concept to sum up as the score for tuberculosis. These weights are determined by how relevant the concept is to the target class. Here we see that the nodule has a very high weight of 8.5, while fracture and pleural effusion has relatively lower weight, as they are not relevant to tuberculosis. So CSR will compare the X-ray with similar cases of interpretable concepts and provide evidence by showing which example it used to support its prediction. So that was a brief on motivation and how CSR worked. Now I will give a little background. So what does it mean by interpretable? One way is to explain the model by concept. So we can take this example. If we say this is a red panda, we can explain our decision by answering which characteristic can describe a red panda. So we can say this is the red panda because it has long body, triangular ear, long tail, and so on. So these are the concepts to describe the red panda, hence explanation by concept. And the models that can explain its prediction by concept is called concept-based models. And the pioneer in these streams of models is concept bottleneck models. Its design is really intuitive, where the model will first predict the concept and then predict the final task from this concept results. As we can see on the top, given an X-ray of a knee, the model will first predict those relevant concepts, including sclerosis, bone spur, or narrow joint space, and then use those concept score to predict the arthritis grade. And similarly for this bird, the model will first predict the wing color, the tail color, the beak length, and so on to predict the species from this concept. However, concept bottleneck models are quite restrictive in practice because they require dense concept annotation in the training data to learn the bottleneck. And post hoc concept bottleneck models address this limitation. They leverage concept activation vectors or multi-model models to learn a concept bank. And this concept bank will be used to train the bottleneck model. Another notable work is LaBO, or language model guided concept bottleneck for interpretable image classification. Here they leverage a large language model to describe the possible concept of a given class. For example, they're using LLM to describe what the axolotl look like, and it answer, and with this information showing that these are the concept for the axolotl, including the limbs are delicate, tail is long and thin. And they do this for all of the classes from the training data and obtain free concept annotation. So besides explaining the concept, one other way to explain is explanation by examples or prototypes. So to predict an image as a red panda, we can show the typical examples of a red panda, like these images. So to make it more fine-grained, we can explain with local examples. So instead of predicting an image as the panda by comparing with other red panda images, we can compare it locally, part by part. For example, we can see the head and compare with images of red panda's head and do it accordingly for other parts. And we call this explaining with part prototypes. And the pioneer on this type of models is ProtoPNet. Here we can see how ProtoPNet is predicting this image, whether it's a red-bellied woodpecker or it's a red cockaded woodpecker. If we look at the left side, in the first column, the model is looking at different patches on the image and compare it with the similar patches from the training set to calculate the similarity score here. And those similarity scores are aggregated with this class connection or weight, which tells us how important a patch example is to a class. And this weight will vary across different classes. And finally, they are sum up to get the score for the red-bellied woodpecker. And this process is applied the same for the class of red cockaded woodpecker here, with a score of 16. So here the score is 32, which is higher for the red-bellied woodpecker, and this is the decision of the model. Another work called ProtoTrees learn a binary tree and traverse the tree to predict. As we can see here, given an image, the image will be compared with different nodes to see if the prototype is present or absent, and will go through the routes accordingly. One more part prototype work is PIPNet, where they leverage contrastive learning of different views of the input to learn the prototype. And they show that this way of learning will produce a prototype that aligns with human semantic concepts. So concept-based model and prototypes models are two main explainable methods, where concept-based models are ante hoc explainable, where the models are designed to learn explainable concepts during training, while prototype models are post hoc explainable, where we try to interpret the model explanation after training. The learned prototypes from prototype models are not explicitly crowded to a human interpretable concept. We would just try to analyze them and try to guess which concept it is reflecting. Hence, we find the concept-based model are more intuitive and more trustworthy because they are grounded to specific concepts that are firstly defined by human during training. However, concept-based model only provide image level explanation. We know that given image, the associated concept of this image to support the prediction, but we don't know exactly where do the concept occur on the image. While part prototype model, on the other hand, can provide more granular patch level explanation, which can be more useful for human. So we propose concept-based similarity reasoning model, or CSR, that is interpretable by design and provides granular patch level explanation by showing example. So it's the best of both worlds. So from the concept-based model, where it predicts the concept as support for the final classification, CSR compares the input with patch level concept example. So you can see here, from this image, it will compare the patches from this image with the patches of different concept example, like triangular ear patches, long whisker, red fur, or white mat patches to predict the red panda. And this is the concept similarity score and maps, where it can show which patch on this image is similar to the concept example patches, and with the score, with how much similarity score. So it can provide local explanation. So we come back to the medical problem. And this is the whole inference pipeline of CSR for a given X-ray. So given an image, we have a feature extractor to extract the feature maps from the image. And then we will project this feature map to a space that is more well represented with concept. And here we will use the concept prototypes to compare with this feature maps to obtain those similarity maps S. And we will take the maximum of these maps to get a score to see if the concept is present or absent on the image. And this score, or concept similarity score, will be aggregated to obtain the final logist of the downstream class. So this is a more concrete example. For this image, we will compare it with those prototype to produce those concept similarity maps. And the higher the value here indicates the more similar the image patch to the patch on the prototype. You can see here, this is very high value, means that this area on the image is very similar to this area on the prototype image. And here we are just take the maximum of these maps to get the concept similarity score and predict this image as pulmonary edema, which is often caused by congestive heart failure, and the heart cannot pump efficiently, blood can back up into a blood vessel that takes blood through the lungs. But as a radiologist, we can look at the image again. Those two concepts of lung fluid and enlarged heart are wrongly predicted because the heart is normally sized here and there's no fluid at the bottom of the lung. So the doctor can choose to intervene or interact with this model because he sees the explanation model of the model is wrong, and he can choose to interact spatially or conceptually. So for spatial interaction, the doctor can tell the model where to focus and where to ignore with the positive bounding box and the negative bounding box here. So this box will form an importance map as the formula here, where we form A, and A has the value of 1 for all of the pixels within the positive bounding box, and 0 for all of the pixels within the negative bounding box, and alpha from 0 to 1 otherwise. And this importance map will be used to modulate all of the concept similarity maps here. And we can see this negative bounding box here is suppressing the similarity maps of the enlarged Hz concept, leading to the deactivation of this concept. And the doctor can also just setting this concept of lung flux to 0 by concept interaction to deactivate the concept. And after the doctor has interact with the model predicts again to obtain the class of tuberculosis that is very relevant with the opacity concept, which is correct. So to learn such model, we adopt a 3 stages training strategy. Firstly, we will train the model to predict the concept from an image. So this is a very standard way. We have a feature extractor and a concept head to predict the image concept. And we will leverage some interpretable method like RedCam or CAM to obtain those concept activation maps. Like for example, here is the concept of the pacemaker, the concept of the nodule, or the concept of the blunt edge of the lung or lung fluid. And after we have obtained those maps with RedCam, we can use those maps to weight the feature maps F here. For example, this green box here is the product of the feature map with the CAM of the pacemaker concept. So it is highly activated here in the region. And we do the same for the blue and the red one. And after that, we will take a spatial sum to get the vector. So this vector will have the condensed information of the concept here. So given a training set of many images like this, where each image will contain different concepts, we will obtain many of those local concept vectors, where each of them will represent the concept. And from those vectors, we will apply contrastive learning to learn the centroids or prototypes here. And these prototypes will be used to compare with new images at test time, like I just showed here. Yeah, so we come to the results. Here we benchmark CSR with other explainable methods, including CPM, ProtoPNet, ProtoPool, ProtoTree, and PIPNet on 3 datasets, including TBX11K, being doctor, not showing here, I'm sorry, and also ISIC, which is a skin dataset. And we're evaluating it using F1 score for classification results, and also the number of prototypes and explanation. And CSR outperform all of those other explainable methods with very few explanation. Because if we look at ProtoPNet, it has a number of explanation up to 3,000. You can imagine if we show 3,000 explanation to a human, although it can be helpful, but it's not very easy to interpret. So fewer number of explanation will be more useful to human. Yeah, besides classification performance, we also measure how if the explanation of the model is faithful or aligned with human interpretable concept with the pointing game hit, where we choose the maximal activation on the explanation map and to determine to see if it lies within the bounding box of the disease. If we look at here on the image, the CSR is the green square and the purple rectangle is the bounding box ground truth. And CSR mostly lie within the ground truth bounding box and achieve a very high pointing game hit rate. We can see that ProtoPNet, ProtoTree, or PIPNet are on part prototype methods. And as I mentioned earlier, they are post hoc method, which the prototype are not crowded to a human concept, So their score is really low, while concept-based model like CBM or CSR has a very high score of pointing game. Yeah. So CSR achieved this result without intervention of the doctor. And in the paper, we also show that the intervention of the doctor greatly benefit the performance of the model, where the concept interaction is more impactful than the spatial interaction. But the spatial interaction will still also yield very beneficial results. After this, I will show you the demo of CSR. Yeah. So okay, so this is the demo of CSR. So this is an image, and we will first predict to classify it into 3 classes: tuberculosis, non-tuberculosis, and healthy. This is the initial prediction of the model, where this is not certain between non-tuberculosis and tuberculosis. And here are the explanation of the model, where on the left-hand side is the similarity maps, and on the right-hand side is the prototype image. For example, here we can see the lung lesion concept has the similarity map as this lung lesion, very small here, and it's showing similarity score of 0.8 with the patch on this prototype image. Okay. And the model also predict this image with fracture here, which is wrong, and had a relative high score of 0.4. So as a doctor, I can choose to reject this concept like I showed earlier and predict again. So after rejecting the concept of fracture, we can see that the model is now more certain of tuberculosis. And we know that tuberculosis is very relevant with the lung lesion concept. So what if we reject this concept and predict again? Now we can see that the model is not certain that it is tuberculosis anymore, and more leaning to the prediction of healthy. So that is how the concept interaction work. Now I will show you how the model can be interact spatially. So this is another image of a tuberculosis patient, and we can see this opacity here is very typical of tuberculosis. And this is the initial prediction of the model. Yeah, the model is very certain that this is a very TB case. So now we will try to tell the model to focus on this opacity region and see its prediction again. As we can see here, if we tell the model to focus on that region, the model is nearly 100% certain that that is tuberculosis. So as I mentioned, besides positive bounding box, we can also tell the model to ignore a certain area with negative bounding box. So what if we tell the model to ignore this region? Yeah, let's see. Yeah, so when the model is told to ignore the opacity region, it is no longer think that it is a tuberculosis case. Yeah, and we have one final experiment where we try to mask everything with the negative box and see the model prediction. Yeah, we might think that the model will predict it to be healthy, but in this case, when we tell the model to ignore everything, it has no evidence of anything. So the three classes has the same score. Yeah. Yeah. So that brings me to the end of the presentation. Yeah.